Okay, we've got a solid disc 30mm wide rotor by 110mm diameter. We've got a tank, a 10 litre tank of compressed air with over 3,250 psi in the tank. We've got a 50 bar regulator, and we're going to slowly crank up the pressure and see what sort of RPMs we get. We don't know what's going to happen, we've never done this test before, so stand by. Here we go. RPM. Then slowly going up with the pressure. Going at about 20 psi. RPM. RPM. Turn the air off. Something's gone wrong. What was loose? We don't know, but something's not right. I can smell burning. That smells good. What? What went wrong? So we're on the wind down now. It's coming down from 7,000. It can't have gone that badly wrong because there'd be a lot more noise, smoke, smell. But I could definitely smell a burning smell. So we'll find out soon what's happened. It's dropping about 30 RPM, 25 RPM, 30 RPM a throw at the minute. Just gone under 6,000. This is the thing with these high speed tests, you never know what's going to happen. Did I tighten everything? I hope so. Did the air expansion move something, loosen something? Was there too much vibration? We don't know, but we will soon find out. But something's definitely happened. Oops, that was a tripod. So we had another camera on the tack, which is handy. By the time you see this, hopefully you'll have a picture in picture. So this is the setup. This G clamps are there, and there's the big boy. So when we started the test, the shaft was touching that needle point. It has switched onto the bottom needle point. I mean, I don't know why we had a burning smell. The burning smell quickly disappeared. So you can see the RPM drop actually that drastic. We're working on the big boy. We're into custom modify some magnets for the Z-axis that sits in there for the Z-axis adjustment. The top two magnets are stuck to the door at the minute, and the top two magnets are stuck to the door there. It's a nice little safe holding place. So yeah, this machine's never been pushed that high before, so the first high speed experiment we've done with that. The 30mm solid disc rotor is experimental. We have a 35mm wide by 110mm diameter one to test next. We're going to be putting some more powerful magnets on the shaft that have got a closer tolerance, so we're going from a 1.5mm gap to a less than 0.5mm gap with the new setup. So it'll be stiffer, more rigid, and it'll be interesting seeing the dampening qualities of the magnetic bearing on the next prototype. It will definitely reach a substantially higher RPM with the same setup, that I can guarantee, because there's less slip, and it'll be interesting comparing the two. It'd be nice to be able to test several different size rotors, but it gets expensive at this sort of size. So yeah, hope you enjoyed the test, and we'll be doing some more testing soon. Just going to let this finish its rundown. See, it's dropping about 5 or 6 RPM a time at the minute. As that gets a little bit lower RPM, the drop will become less and less. So the next challenge will be figuring out what we should have done differently for when we do the next test. One suggestion is that the needle point that wasn't touching should have been wound in a little bit closer, and then perhaps it wouldn't have happened, and we won't know until it stops. So let you know if there's any damage. There might be a little bit. There wasn't any drastic noises. There was a little bit of vibration, nothing crazy. So yeah, we'll find out soon. So we're at 14, 40, 37. So dropping 4 RPM a second roughly. You can see there's a little bit of wobble actually. And it actually caused the tachometer to jump off. It's a bit hard trying to hold the camera and do that at the same time. So yeah, this big boy's looking good. That's the back face where the Z-axis goes there. So it's not on at the minute, but So that's got an adjustable magnet or magnets that go in and out of the face, into that face, that come in and out of here, and that interacts with the magnets that are on the shaft there. So it'd be interesting seeing if we can achieve that. Feel good?
Yeah.
Cool. So tachometer's back up and running, and we're down to still dropping 4 RPM a second, thereabouts. 3 RPM. Yeah, this will get less and less. So, going to end the test there, folks, for the camera, and we'll give you an update and we'll find out what went wrong. Bye. Okay, folks. So the strip down was that we found what happened was this part of the rotor slightly touched the acrylic casing during the test after this nut wasn't thread locked, so a little vibration that came undone because it's not an eye lock. Basically that adjuster is just exactly the same as this. This is from this side. So we've got a stainless adjuster, a stainless 316 locking nut, and these are tungsten carbide flats and tungsten carbide needle points there. So same on this side. So it was standing up that way. So this was at the top. So what happened is that nut came loose. The needle point was already sitting on the top carbide flat, and because the nut came loose, the adjuster wiggled up. So the rotor moved that way, touched the casing, got a bit hot, and then shot back that way. It didn't hit the casing there. The bottom needle point came into contact with that, so that's why it was able to keep going without anything too crazy happening. But you can see it in the video when the rotor drops down. So that's why I could smell a little bit of burning. So it wasn't anything massive that went wrong. A little bit of thread lock on the adjustment nut next time, and we're golden. So it'll be interesting to put the 35mm wide rotor in here. This is the 30mm rotor. It's not going to have such big gaps. I'll show you the gaps that I'm talking about. So you can see there gap. I mean, that's touching. If I push it over that way, I'll just zoom out a bit so you can see. So there's the gap. So originally this was 35mm and now it's 30. So you're going to get less slip with the 35mm rotor, and the 35mm rotor has also got smaller balancing parts on the side. I'm just going to grab that so you can see it. Hang on. Okay. So there's the 35mm rotor, thanks to Andrew Salberg. So you can see the difference in width. So yeah, this one's got the upgraded magnets, thanks to Alex. This one's got 25mm diameter magnets, and the gap inside the magnet bearing inside there is 29mm. So the new one, the magnets are 28 mil that are going to go between there and there, and circlip goes here, washer goes here to allow you to get circlip pliers on without getting stuck to the magnets. So that's why these nylon washers are there. So circlip goes there, nylon washer there. I've got 12 5mm width magnets there, so 60mm wide, 28mm diameter. So that's going to give 1/2 mil gaps in here. The magnets on this one are N42. The magnets that are going on here are N52, which is the highest grade available to the public. So the whole shaft is going to be stiffer in the assembly, and this rotor, because it's this isn't necessarily the optimum width for a single disc rotor. That's depends, you know, depends what you're using, but for air, this is definitely better than this one, and you get a lot less slip. So the same test that we did with this one, if it was exactly replicated with this one, the RPM would be considerably higher. So I'm looking forward to getting that installed and doing some testing. Looking to turn this apparatus into part of the balancing apparatus and applying Tesla's balancing principle to balance this rotor. So yeah, be looking forward to doing that. So I'll keep you updated. Thanks for listening.